Imagine a digital design that clears every hurdle, verifying perfectly in the simulator. But the moment it is manufactured and powered on, it fails completely. To understand why this happens, we have to look at the strict physics of combinational logic. In a purely combinational circuit, the output must be determined solely by the current inputs. There is no clock cycle, no state retention, and absolutely zero memory. The problem is that we don't build these circuits with soldering irons. We write code. And this exposes the central engineering trap of Verilog. It is merely a hardware description language. When we write procedural, software-like statements, a synthesis compiler must translate those abstract descriptions into a physical netlist. The compiler is forced to infer physical hardware intent based on how the designer arranges the text. If the compiler infers the wrong structure, the silicon fails. Advanced combinatorial design is therefore focused on strictly restricting that ambiguity. Modern design methodologies utilize system Verilog semantics to create a more rigid mapping between the software model and the hardware netlist. By restricting how the compiler interprets procedural code, engineers can target and eliminate the most common sources of combinatorial bugs. We can observe this ambiguity by looking at the lowest level of RTL abstraction, data flow modeling. This is typically done using the continuous assignment statement. When you write an assign statement, you mimic the continuous voltage propagation of physical logic gates. The moment an operand changes, the target net updates instantly. But this one-to-one mapping breaks down at scale. If you try to build complex nested logic, like deep multiplexer trees, using only data flow assignments, the code becomes visually unreadable and difficult to maintain. To handle that complexity, engineers use behavioral modeling. This relies on procedural blocks, like the always block, and high-level structures like case statements. Inside a procedural block, the code evaluates sequentially. It reads step by step from top to bottom, heavily resembling software languages like C. This creates a semantic gap. Procedural code evaluates sequentially in a software simulator, but it synthesizes into parallel physical hardware. This disconnect between the code's sequential appearance and its physical reality is where bugs are born. In the legacy Verilog 2001 standard, designers were bound by strict rules for variable types. If you used continuous data flow assignments, you had to declare a wire. If you drove an output from inside a procedural block, you were required to declare a reg. The problem is that the reg keyword is a misleading term in hardware design. Declaring a signal as a reg does not guarantee that a physical, state-holding hardware register will be inferred by the compiler. In fact, a reg variable will routinely synthesize into a basic combinational wire. The final physical structure depends entirely on the procedural context surrounding it. This creates constant syntax friction. Engineers shifting between design abstractions must rewrite variable declarations back and forth from wire to reg to satisfy the compiler. The system Verilog standard introduces a universal data type to resolve this, the logic keyword. The logic type can be used in almost all variable declarations, replacing both wire and reg, whether the signal is driven continuously or procedurally. Adopting the logic type stops engineers from making false assumptions about the hardware based on variable names. It forces the compiler to deduce the physical intent strictly from the actual logic structure. Beyond data types, behavioral modeling comes with a strict simulation rule. A procedural block must completely reevaluate its outputs anytime any of its inputs change. This Verilog 4-to-1 multiplexer has an explicit sensitivity list on line 7, dictating when the block executes. The engineer must manually track every input. Adding a new control signal below, but forgetting to update line 7, creates a critical discrepancy. In the software simulator, this omission means the block won't trigger when the new input changes, potentially passing false positive tests. However, synthesis tools prioritize logic requirements. The tool recognizes the hardware needs that input, ignoring the broken list and physically wiring it anyway. To stop this simulation mismatch, the Verilog 2001 standard introduced the always at star auto-populating list. The wildcard asterisk tells the tool to automatically include all right-hand variables. But while it fixed list omissions, it masked a more subtle structural error. The ironclad rule of combinational logic is that an output must be explicitly defined for every possible input condition.
Suppose you write a procedural if-else block to control a signal, but omit the final else statement to handle the default condition. When the synthesis compiler evaluates this block, it encounters an undefined state for that input combination. Because it lacks instructions on what to do, the compiler is mathematically forced to hold the previous value of the output. Holding a previous value physically requires memory. To satisfy the logic, the compiler inserts a level-sensitive latch into your combinational circuit. In high-speed synchronous pipelines, this hidden latch is highly problematic, introducing asynchronous delays that disrupt timing closure and cause data collisions between synchronized flip-flops. The legacy always block accepts this code without issue. It compiles the error, never warning the designer that their combinational block now contains memory elements. System Verilog addresses this by introducing the always COM procedure. The always COM block acts as an explicit architectural declaration. It informs the compiler that the following block is intended to be purely combinational. This creates a strict contract with the synthesis tool. If the compiler detects an incomplete assignment that would require a latch, it will no longer silently infer memory. Instead, the tool throws a fatal error during compilation. It forces the engineer to resolve the ambiguity before the design can move forward. By identifying these logic gaps at compile time, always COM ensures that the physical silicon remains purely combinational, matching the behavior of the software simulation. Once a combinational block is functionally secure, it must be made reusable across different chip architectures. When designing scalable modules, hard-coding specific integers for bus widths creates a fragile codebase. If the data width changes, every static reference in the routing must be manually updated. System Verilog solves this with native math functions, most notably /clog2, which calculates the ceiling of a base 2 logarithm. This allows RTL to dynamically calculate exact vector widths based on generic parameters. If a multiplexer requires m inputs, clog2 determines the exact select lines required. This mathematical scaling happens during elaboration, locking in the logic's physical dimensions before simulation or synthesis begins. Parameterized math functions allow logic designs to scale to any width, while removing the risk of human calculation errors in the physical routing. Reliable silicon synthesis requires the total elimination of ambiguity between human intent and machine interpretation. Using the logic type removes the manual syntax friction of legacy Verilog and prevents incorrect hardware assumptions during design. The always COM block enforces architectural intent, protecting the hardware pipeline from silent latch inference and timing failures. Together, these System Verilog upgrades force software simulations to align with the physics of the target standard cell library. Advanced design is achieved by authoring code that is mathematically impossible for the compiler to misinterpret. By constraining the tool with explicit semantics, we guarantee that the final manufactured silicon is exactly what we verified in simulation.